All right, welcome back to Anoma Research Day. This is Anoma Research Day. If you are not here for Anoma Research Day, you are in the wrong place. Check your URL bar. We are on the very last presentation, or the very last major presentation of the very last track of this long but rewarding day. And the presenter of this very last presentation will be Tobias, talking about communicating systems of Anoma engines. Will he use the same definition of the word engine as our previous presenter did? If you don't stay, you won't find out. Tobias, take it away.
This is awesome. First of all, I'm so glad that we have this, and I'm part of this, and we can have this together. And yes, first of all, hello out there. I'm Tobias. I'm part of Heliox. Thanks for taking the time to listen. And if you have questions, yes, you have to do it. You have to write it into the chat, and then somebody will relay it. And I'm looking forward to questions anytime, basically. Right. Now, yes, exactly. Why am I here? Have one simple goal. One. Well, first of all, we have to finish on time because then it's dinner. But, well, content-wise, it is that we have to get down to these engines, what they are, and why do we call them engines, right? That's the real question, actually. Why do we call them engines? So that's the hard one that I'm going to go light. So it's basically history that I've affected. But yeah, what are these engines? And now I have to, at this point, adjust my script. As Chris asked, well, you cannot just, in the context of Anoma at large, ask a question and say, what is the definition of so and so? You have always to augment the question with which version number. Is it v0.2? Is it v0.3? Is it v1.0? Right? And that's basically the point. So I will give you one definition of engine at the end of the talk, which covers like one central point of engines that I think we should have, and I also add something new. However, I should give you a little bit of context, like Anoma, what is it? And so on and so forth. So, right, on the slide, you keep seeing this Anoma in the middle, and that's the protocol for coordination between these four agents that you see around. So, and what's inside Anoma is these engines, and the engines essentially make Anoma work. That's the short version of how this should be, on the big picture should be. So we have these engines, and they connect to Anoma through the engines, and the engines do all the complicated communications work in terms of sending messages. What you actually see on the picture is an example of a very old protocol. It's the token run protocol. I didn't memorize the IEEE something something name, but it's very simple. So you have a bunch of participants that you see on the outside. They're connected to these engines, which are called interfaces. And so through the what's happening inside the ring is that the engines just pass a token around, and whenever one of the participants sees the urge to send a payload, they will just grab the token. The engine will send the payload around to the next, to the next, to the next, until it's once around. And once I have received as a sender the same payload, I'm sure it's distributed to everybody and can give back the token. Token circulates and so on and so forth. That's one protocol. And Anoma is a protocol. So, and we have the very same abstraction. The only thing that we change is that we don't have a hardwired network, but we have a network. And so, what I'm going to do to really explain what engines are is first start with a quick recap of what distributed systems are by the textbook. Right. So, and we are in land of message passing concurrency. Who has heard in this audience here or online? You can put a 1 in the chat if you have seen it online, and a 2 if you haven't. Online, who has seen message passing concurrency? Hands up. Who wants to give a definition of it? Thank you. Yeah, but you just had your hand up. Come on. Okay, not fast enough. Yeah, so it's very simple. So we have a bunch of processes in message passing concurrency then, but these are basically going to be our engines. And they just communicate with each other indirectly through a network. And the network is happily accepting messages from each of the participants, and it looks at the message and magically knows where it's going. So each message has addressing information. The interesting thing and the difficult thing is about the network is like, what assumptions do we make? What do we want to do? And here we had a wonderful talk by Jamie on the behaviors of processes, but we can do exactly the same game probably in terms of message logic concerning the network. The simple assumption typically is that each message sent will eventually arrive at the destination. However, the order need not be preserved. That's message passing concurrency, simply. So far, so clear? Great. So now, the new things that we go beyond something that I will explain later is that we also want this interaction with the user. Roughly something that has been also given in the very refreshing talk of Jeremy, like the user wants to interact with the system in a meaningful way. We just say like, yeah, the user interacts with the system, and we are on the most abstract level. It's a direct interaction between users and engines. So then, also in the talk of Jeremy, we had this fact that this necessity that we want to have new engines spawn, new participants join. And this is spawning an actor model language, right? So that's what we want. So there's two more things. We add time. I'll not talk much about it. It's essentially vector clocks. It's figured out. The one thing that I will touch a little bit more is on the computability of these engines. So we're not doing like the fully expressive actor model where engines can do whatever they want, but we want to have these engines that just computers essentially. Right. And that's Alan Turing, by the way, from Wikipedia, the picture, so I don't infringe on any copyrights. Great. So far, so good. So, right. It's late. It's very late. So we'll go a little bit for storytelling time. So I have this promise, and I will hold it. And this is my promise of my talk. I will explain in the end the main idea of what engines are. So, but the engines are this weird thing that's somehow inspired by this stuff. I've joined Helix about, I don't know when. Who knows? You maybe. Was before lovely Adam. Adam was later. It's about 3 years actually. And I don't tell the whole story. It's going to be too long. But for the engines, it was started by, I think, the specific point in time was like when I started looking at StateWrite, which is written in Rust, which is a language that then was the language we were using, everybody, right? And right now we don't anymore, everybody. So things have changed, right? So there's a long trajectory we're having here. So, and then, well, I'm learning the actor model. I've heard like with Jonathan together. Oh, I forgot to say, joint work with Jonathan and Anthony, whoever he is, and it's great. So yeah, so we looked at the actor model, and it's not the actor model. It's just a whole zoo. It is just a whole zoo. Well, you can say, well, there's the first thesis, and maybe that's your Bible then, but then there's for sure at least one other person in your neighborhood that has a different opinion of what the actor model is. So it's just not there. So maybe one of the reasons why we call them engines is that, not actor. And the other one is from distributed systems land, and I'm pointing at Isaac, state machine approach. Right, that's the other big one. I quickly mention in passing the temporal logic of actions, not only because Jamie has mentioned it, but it is having this very nice word action, that somehow these engines perform actions, and the simple actions like sending messages and state updates, spawning new engines, checking time and stuff, right? And then another thing that I just recently learned about that it exists is so-called even condition action rules that actually come from actor database management systems, something that I've never heard before, but this is a beautiful name because it really says what's going on. So the engine looks for an event to happen, then it checks a condition, a predicate on state, and then based on that, it decides, should I do something or not, and if so, what, by the action. And this is actually pretty close to the definition of engine. So, already comments, nodding people, that's always a good sign. And there's Anthony, hello. Great. Yeah, state machine approach is really the point, and here I am changing gears. In that communicating finite state machines, I have to do this trick. That's just out of curiosity now, like who has heard of those before? Yeah, so who has had a course in automata theory? Yes, more people. Who has used?
They didn't cover CFSMs in that course.
Who has used the tool GJF Lab? So just in case you want to know about automata theory, there's two ways. You go now to the different tab and you type JF Lab and you download the tool and play with it, or I can tell you in 3 slides what's going on. 3 slides, right? It's late in the day, long day. We have already, all the brains are already exploding almost, but 3 slides for this. So, slide number 1, Moore machines. It's a classic textbook example of state machines, finite state machines. So what do we have? We have a finite number of states, and the graphical representation is the following. So you make for each state a circle and you write the name of the state upstairs. Then, besides these states, you have transitions. And the transitions always involves 2 nodes. And you will have, in the first node, you will have upstairs the state where you are right now. Then you have an arrow that reads what is actually being read, what is the input, the message you receive. And based on that message in your state, you decide to go to the other state. And that's already then done. And once you arrive there, you look, okay, what should I do? Oh, I sent a message to somewhere, the output. And then you can look at a whole collection of states and transitions. And moreover, you designate one state, the state in which the machine is right now. So we have now 3 states, listen, copy, and send. For example, if I'm in listen, and I receive a 2, then I will transition to the state copy and output a 2. That is really like, that is like in every textbook on automata theory. So what is the next step is, how do we make these machines talk to each other? Oh, right. There's always, so the experts out there will say, but no, that's not true, it's not a Moore machine. You don't have a total transition functions. And yes, you're right. We have just a partial transition function. But that's all right. We can do that. But just for the record. Okay, good. Okay, now we want to make these things communicate with each other. First thing is like, we have this network there, it's back, and we give names, A and B, for the participants. And each of A and B are one of those Moore machines. So, attention, here they come, 2 Moore machines. So it's essentially the same as before, just the input and output labels have changed. For example, if you look upstairs and the listen state, if I receive a 0, I also get the information who has sent the 0 and actually to me. That is a technical convenience that it's there. And the question mark indicates I'm reading, and the explanation mark, the bang, is the sending. So, for example, if it were that we put this token into the network saying that B is just sending, B is done with sending, and now B has put the message that to A that the token is there for you to grab. So what will happen in this state of the 2 states, so the upper machine, both machines in the state listen, and the token is given back, so to speak, from machine B into the network, and now machine A can take the token by reading the message B is sending 0 to A, and it will transition by B. I read 0 from B, and I transition to the state send, and accordingly I have to then put into the network, I consume the message and I put back into the network as machine A my send, so I send my payload, very boring here, to the network. And if you look at this closely, this is actually the token ring protocol I showed you on the first slide for 2 participants in a certain variation. Great, that was slide 2. Questions, comments? Everything clear? Fantastic. Oh.
Just a technical question here. So B is baked into the appears to be, as illustrated, B appears to be baked into the syntax of A.
Baked into the syntax of what?
Yeah, if I look at the A there, it nominates the B that it's going to speak to.
Mm-hmm.
So if I replaced B by C, that would be a different Moore machine.
That would be a different Moore machine, and probably the message would never be delivered because there's no such machine.
Okay.
However, this question will be much better explained if I switch to the next slide. May I switch? Okay, great. So now there's the third thing. The label transition system semantics. I will come way at the back why we need semantics, but And this again is basically the last point of recap. So choreography automata, if you look, is actually where this is taken from, but you can see this over here. This definition is textbook just adapted to our own machines. So we have our transitions from states to other states if you read a message. So machine AJ is getting a message from machine AI, and the message called M. As a response, I transition to the next state Q prime, and I send a bunch of messages, possibly 0. So if this happens in the context, well, the context is not just the machine itself, but actually a finite set of named machines, as I call them. So we have a bunch of AIs. These are the participant identifiers, and they are mapped to actual machines. And moreover, the network is given, the current state of the network is just a finite set of messages with sender and recipient and the payload, right? And then this transition here, I can lift it up to the system such that if it's the case that this message AI sends to AJ to M is actually in the network, that's the first clause, like I pick this message out of the network randomly, essentially, if you will. Then I update the state of the machine AJ according to this update of the partial map, technically. And finally, I update my set of messages, right? So I remove the message from the message set, and I add the new messages as they are sent by machine AJ. And this is useful, this label transition semantics, because you will need it for the same reason that we have actions in TLA+. These labels and the transitions are then essentially action labels, and you can specify properties of the composed system such that for each A message will be responded eventually by a B message and stuff like this, as it's common in the temporal logic of actions of Lamport. Questions, comments? Too much, right? This is a little bit too much for that. Oh no, Robert is still awake. Fantastic.
Your diagram.
So your diagram there in the bottom right that talks about AJ's communication of its state machine with its mailbox,
So
and
exactly,
Q prime, which belongs to.
No, this is just like a machine AJ, which has two states, Q and Q prime.
Yeah.
And it is in state Q. Oh, well, I cannot point. I was just told I have to do this now with the mouse, sorry. So AJ is in the state Q, and it, as per indication of this arrow here, and it will read the message and transition in the state Q prime, and accordingly send messages.
Send, got it. But what do you have the arrow back to Q for then?
To indicate, well, the arrow that comes out of nowhere is the arrow that just indicates the current state. And that is terrible.
That arrow
terrible.
comes out of nowhere. That's not going
Yeah,
back
that is
from
like,
Q.
yeah, the arrow should come from downstairs, but then
okay.
the
Then
slide
now
would have a, yeah,
now it
that
makes sense,
Yeah,
thanks.
that's an improvement of the slide. Yeah, thank you very much. It just looks weird. It's true. Yeah. Thanks for asking. Cool. Then, yeah, this is like the most technical part of the talk, and then now comes the fun part. So, so this is like textbook choreography automata, and now, actually, I'm presenting now another 3 slides, the paper that we've just pushed yesterday to our fantastic ART reports as organized by Jonathan. You should go out there, ART reports, Anoma, good stuff. And we have this new report, and we do now a couple of things with these machines, because so far we're just finite state, we need more. So, in short, we just want to also spawn these new things. But that's very easy. In this case so far, I just enumerate all possible machines, give them a number, and if machine A wants to spawn the machine with number n, it just outputs an additional label and saying like, well, I as machine A want to spawn the machine with number n, and it should reside and be addressable as machine B. I should make sure that B is free, but that's something that you can read in the paper. Very easy. Slightly more interesting is that, well, so for its finite state machines, and I can easily describe them just by tables. Like if you go to the original paper of Moore, he will just talk about actually these tables. He will not talk about transition functions. It will be just tables of state transitions. So now I have a countable state space. To describe a function from a countable state space to something to a countable state space, it's a little bit more complicated than just giving a table. However, that has been figured out. You don't have to invent the wheel. It's done. It's computable functions. And between countable sets and thanks to Gödel, we have at least one numbering of all these functions that we can use. You remember that I said I need to enumerate all these machines to be able to specify which new machine I want to spawn. That's it, spawn someplace. Great. And yeah. So, ta-da, here's the paper. All the details, including the timed case about original, will not talk here. So I will take 2 minutes here. No, I take the short break. So yeah, that's the paper, joint work with Anthony, and it's all written up. That is essentially now the point. We get ready for the actual stuff. I can tell you a little bit more, just to prepare you. So, you remember now that I told you about these computable functions. And they're beautiful because that's what you're going to do with the computer. And they can do a lot of things, but many things you cannot do. But the hardest part is like to actually present these computable functions. So if you have a simple function like +1, it's very easy. But already writing a sorting algorithm in any programming language, if somebody gives me the code of I don't know, a first-year student of university that describes a sorting function, I'm not sure it's really a sorting function. I just read the code and I'm going to find a bug. And then what is this function actually? It's really hard to describe in syntactical terms these functions. Yeah, in theory it's very simple. I just give them a number because and how do I get the number in the case of a specific programming language? I just essentially look at the number that's encoded by the code if I represent it as a number. So basically, if I'm just at the point where I have to specify these transition functions as just any computable functions, it's very, very difficult, in my opinion. So what do we do? Right, engines. And so basically, as the countable state spaces are like typically structured, I might do something clever. I might find out, well, the state space is huge, but I can kind of discern a finite number of equivalent states, and I just say like for each of these equivalence classes of states, I describe via an action what I want to do. And this is the example. So for example, if I have all the states that are kind of touching green, if they receive an A, then they just move to the right. And in the orange states, it's like if they receive a B, they go down, and if they receive an A, they just go to the next row. And this is an example of what we call a guard. And a guard consists of a predicate that says, like, for a message in the state, whether something should happen, and if something should happen, then it moreover describes what should happen. Right, and the engine definition, unversioned, and just the basic idea, and basically I'm very, seeing Jamie there, this is not a definition, sorry. But it could be a definition, and it's not the definition, but it's maybe the engine definition version 2.1 or something, version 0 to 1. So we have a countable behavior, that means, and it's very simple, two things. So we have our engines that are extended to the countable behavior as described before. So we have a transition and output functions that are just computable functions as per Turing and maybe enumerated with Gödel numbers. So, but we want a little bit the finite state machines from the 80s because they're very simple and they actually were used to define what a protocol is. A protocol was defined as a communicating finite state machine. So we want that back. And what do we do? Yeah, in good cases, we can kind of recover the illusion as if we had just finitely many states, or at least we try to approximate with a finite number of guards that describe the behavior. There's one specific special case. If you just provide one guard, you exactly recover the original definition of a Moore machine. It doesn't make a difference if you have one guard or you just have the Moore machine itself, but you are allowed, so to speak, to be a little more general. And there's a lot of trouble that I'm not talking about like what happens if several guards don't want to go with each other, but this is the very simple idea of engine definition. It's just a machine with countable, computable behavior and finitely many guards. How much time do I have left? Don't worry about the time. Dinner. Who's already hungry? So just to give you a flavor, like that, this is connected actually to the literature that I have alluded to before. So this is a beautiful paper for reasons that you will see when you go there. that here's just one of these rules that actually occurs in larger context. And what I want to, maybe with the mouse even, show here is that it's really this on a certain condition, on a certain event, if a condition is true, then I do something. And it's a very nice application. And moreover, it has a presentation in terms of patronets, and that's why the paper is awesome, because I love patronets. Okay, so if you go to Wikipedia and look up even condition action rules, you will find this word trigger, which is actually the one that we use instead of event, because event again is a little bit overloaded. Last but not least, 2 sentences of tempo logic of actions. There we have actions defined in a fun syntax if you have the right spirit. It is possible to use this, but it's well known to be hard, and that to describe, like, so it forces you that every variable denotes a set, and then you force yourself to somehow give a relation between assignments of sets to variables before in the old state, and then somehow you describe how they update. And if you forget to say that something stays the same, anything can happen. So it's really like the ultimate foot gun for specifying system, but it's executable. However, it has in principle this nice built-in notion of a guard, in that if I pair the action with the enabled action predicate, then I get the corresponding guard in the sense that I have described before. To conclude, I have given you the basics of message passing concurrency and explained to you what a state machine is and how they can communicate with each other. And I have quickly advertised what are the extensions that we want to have to describe our Anoma protocol, in terms of that we need to dynamically create new engines, very much like in the actor model. We want to act clocks, which is a technical necessity more than a difficulty. And the one thing that we actually leave out as future work to be detailed is how we want to interact with the user. Right. Then there was this promise. I explained to you what engines are, and really the simple idea that everybody could and should understand, I hope. Please. Yeah, but I have seen so many good stuff. I mean, I feel like I'm the most stupid person in the room. Like, so many awesome discussions. So I'm sure it's here, but out there, like, if you have questions, like, tell me, like, was this a good explanation of engines? Maybe a thumbs up, or like a question like, what is this anyway? Like, or where should I read up? Like, I'm looking forward to your questions. So the 2 ideas are, like, I extend the behavior of machines to be computable, and I allow for extra structure, or I essentially ask the specification person to give this extra structure in terms of finitely many guards, very much like Killer Plus. Very, very important is, why do we do this? We want to specify Anoma. That's what we do day to day, and we want to describe what the Anoma system, the Anoma specification, the Anoma protocol, great. The Anoma protocol does in terms of these engines, which are not fully declarative, but they have the advantage, similar to TLA Plus, that they're in principle executable, so that at some point in time, it could actually be that we have not only the Anoma specification, which is operational in the term as per the LTS semantics, but we actually can execute this LTS. Maybe not in the most efficient way, but as a reference for any other specification. So that's the idea, and it's just the starting point of a journey, I think, that we are all on here in the room. And please ask questions.
All right, thank you, Tobias. Do we have questions from the live audience? Yes, Artem.
Thanks so much for a wonderful talk. So I remember we talked about at a certain point how this, for example, differs from the classical Erlang model, right? If we talk about trying to think of gen servers, right? Gen servers have handlers, and looking through Armstrong, etc., it turns out that it has guards. It has something that we could kind of talk about like guards, but it doesn't allow for a general predicate, right? Those handlers don't allow. So the engine model allows for those general predicates, right? And they sort of almost save space. So from what I understand, there can be several guards activated for one message. Is that correct?
That is exactly something that is out there. So when I was originally bringing up this idea, I was, and also I can actually cite quote Anthony saying like, right now we actually do this mostly that at most one guard is active at any time.
At
Because
most.
At most one guard is active at any
Uh-huh.
time. Because that's the easy case. Because if like then the next step would be, and then this is really like up to research, and these are design decisions that need to be made and are important. What do we do? Like, do we want to allow for several guards to be in conflict? In which case, I need a conflict resolution strategy such that a serialization is happening. And that's not a serialization in the terms of Isaac. It's just like I really fix an arbitrary order in which they are to be executed. In something like, yeah.
So wait. So is the point that currently you just ask that every guard should not? So is it that you pass the message through all the guards, or is it you pass them linearly? You have some ordering on the finite amount of guards, and you kind of stop and execute the action of the first one, which is matched. What's the behavior, in other words, if I specify 2 guards, like if I send an integer, which is, of course, both an integer and is even, if I send 2, and I have guards on that message that checks, is the message an integer and is the message a 2? What happens?
You want to answer that?
I mean, we are investigating, like, yeah, there are different strategies to evaluate guards, and we are investigating which is the most convenient, or if the model actually can encompass all the strategies, the possible strategies, right? So this is one thing. And the other thing is that this differs, and maybe I'm mistaken here about Erlang, but we are constraining the space of function, right? Because we are saying computable behavior, and if I'm not mistaken, in Erlang you can have any function, right? The handlers, the message handlers can be any function, right? But we are saying here that we want just total functions, right? Because we want to predict the system how it will react to messages. Like, we don't want, we want, for example, to have the engine behavior to always respond and not getting into a loop, right? We always want terminating functions, total functions. So it's different in that sense. That's another thing that we forget to mention, but it just...
What I would add here, like, sorry to interrupt you, is that we are actually writing up another art report on how we would do this in more concrete terms. So that this very general idea of that we start out like with the idea of a state machine, we have the finitely many guards. And what actually is happened, so to speak, step by step in a more refined model is actually in the process of being written up. And we should probably just keep going our weekly meetings and everything, and just keep working it out so that we have eventually a version that will stabilize.
Yes.
Yeah.
Other questions from the live audience?
Great presentation, Tobias. Thank you. Especially the diagrams. How do engines relate to the resource machine?
They're completely orthogonal, I would say, in that the state is completely arbitrary, except for that it's countable. I mean, unless we need like resources that store real numbers, it's all good.
Jeremy, take the mic, please.
Hi, thank you for your talk. I want to have a follow-up question based on what Artem asked, because it had me thinking, could multiple guard evaluations be viewed as like a choice point where, because as far as I understand, at least in this engine model that you have, you've modeled like all the engines, you've basically modeled the entire system. And so you actually know the entire system state at a particular point. Could you model 2 guards matching as a choice point in which you could always backtrack to if, let's say, computation fails in some way, or maybe you're not satisfied with the result? It was just something that came to my mind when I was hearing the discussion.
So concerning choice points, I rather think about if there's a specific choice to be made. Well, like you said, like there's a general situation of there's 2 guards that potentially like competing activated. I mean, if they're essentially like independent of each other. I can just execute them in parallel and nobody will cry, hopefully. Yeah, maybe it's also the wrong thing, but just in case. Like the interesting cases are like if I have essentially two choices. So there's two variations. So first of all, the programmer or the specifier has made a mistake and we should give an error and a warning, or we want this. If you want this, why don't we just ask the user, what should we do? So the main point that I actually didn't hark upon here is that what we want is that each behavior is deterministic. I mean, it was implicit in my presentation that didn't hark up in. So we want to have that actually, if there's a choice point, you rather ask the environment what to do. It could be also a random number generator or something. But, and this is if there's really a choice, then it should be exposed to the user. Or you have a resolution saying, like, if I have two things, then I have something like a precedence and I resolve it that always in the same way. But I don't make a real choice then. It's just like a conflict resolution strategy. Does that make sense?
Yeah, roughly.
Great.
Other questions from the live audience? Questions from online? Okay. Then thank you again, Tobias. We will have a very short break.